Welcome everybody to today's webinar on RISAConnection 3's new features, which are the design of stiffeners and of non-concentric brace connections. Today, the programs that we're going to be taking a look at are RISAConnection version 3.0.1. This is an update that recently came out for connection. And then RISA 3D version 11.0.2 and RISA Floor 7.0.2. These are the latest versions of our programs, and we're going to take a look at how those integrate together. But we're not going to be spending a lot of time on integration in today's webinar. Instead, rather, we're going to be focusing on the technical aspects of stiffeners and what they're needed for and how to use them within a program. And then later on, about some technical aspects of non-concentric brace connections. Now, all the code references that I'm going to be giving today are out of the AISC 14th edition manual, although a lot of these concepts are identical in the 13th edition manual as well. And RISAConnection and RISA 3D have both the 13th and 14th editions, so whichever one you want to take a look at, it's still valid either way. We're also going to be taking a look at some provisions that come out of AISC's Design Guide 13. And this is the design guide all about column stiffeners for moment connections. And this is applicable for both wind and seismic. And one thing I'd like to point out about Design Guide 13 is that this is an older design guide, and a lot of the provisions that were written in this design guide were based off of the LRFD 2nd edition manual. And so a lot of that has been sort of superseded or changed somewhat in the 13th and 14th edition. So what we actually had to do in order to implement a lot of these provisions into our software was to determine how the equations mapped over between the LRFD 2nd edition, which is referenced in this Design Guide 13, as opposed to the newer editions of the Steel Manual. And so we had to adjust some feed factors, we had to reformat some equations, and you'll see that within the program. Now to start with, I'm going to talk about the moment connections, and we're going to talk about the need for stiffeners on columns and where this comes from and how we apply these within the program. Now to start with, one very important thing to consider is what is your moment arm when we talk about the forces that occur on the column. Anytime that we have a moment connection, we have to consider that there's going to be a tension and a compression applied essentially as point loads onto the flange of that column. Now, in the case of the flange plate moment connection, what we take a look at in terms of forces applied to the column is a moment arm that includes not only the depth of the beam, but also half the depth of each plate for those flange plates that come on there. Now, when we take a look at the end plate moment connection here, you can see that the moment arm is actually a little smaller in this case, because rather than the forces applying at the center of these flange plates out here, we actually have to take the depth of the beam and subtract half the flange width on both the top and the bottom to determine that moment arm. And the same is also true for the directly welded moment connection. We also take a look at the depth of the beam minus half that flange width. So you may notice as you're working within the program, as you switch between different moment connection types, you end up with a different flange force because you actually have a different moment arm that's acting there. Now, I'd also like to point out that we use this value N within the program, and N is the flange bearing width that occurs on the column. And so what you have to consider when you do this is that for different moment connection types, you're going to have different flange bearing widths. In this case, what we're taking a look at is the flange plate moment connection. Now, if this flange plate is welded with a fillet weld, then what happens is that point load that we have bearing on the flange actually spreads out by a distance of 2 times the weld size into the flange. However, if we have a CJP weld or a PJP weld, then we have a smaller area where that load is acting on the flange of the column. So your flange bearing area is reduced somewhat in going with these larger, CJP or PJP type welds. And so you may encounter a situation where your connection seems like it would be stronger with the CJP weld, but in actuality, when it comes to things like flange bearing, you've actually made it weaker somewhat as opposed to spreading the load out with a fillet weld here. Now, in the case of end plate moment connections, it's also the similar idea. The CJP weld is going to result in a smaller flange bearing area, this N, as opposed to the fillet weld. And then lastly, the direct weld, this is always going to be a CJP weld, and so your bearing area is just going to match the beam flange thickness in all cases. Now let's talk about the limit states that we're concerned about when we're taking a look at stiffeners on these columns. The first one we're going to discuss here is the column flange local bending. The idea behind this is if we're taking a look at this column down in plan view sort of cross section, if I place a moment connection on the flange on the bottom of the screen here and pull back on it, one of the tendencies of that column is for the flange to bend outwards due to that moment. And so we're going to have to put in a stiffener if this bending gets to be too much where the column can't handle this, and that would be your flange or transverse stiffener. Another common failure mode is the column web local yielding, and each one of these failure modes is listed as a separate limit state within the program. In the case of column web local yielding, what you're looking at is, imagine that we have a compression now placed on this column, so this would be the compression arm of the moment connection, and what happens is that pushes so much on the web of the column that you actually get localized yielding in this location of the web here. That's considered another failure, also preventable by transverse stiffeners. There's a column web crippling, and this is a local buckling of the area on the column flange nearest the moment connection, where we get this buckling that occurs right here due to the compressive arm of the moment connection. And then we have column web buckling overall, and this isn't as related to the compression arm so much as just the overall axial force coming into the moment connection. So if you have a beam that's part of your moment frame that's carrying an axial force as well, pushing against the column, you can get a failure mode where it actually buckles the entire column web outwards, as you can see here. So these are some various limit states that can be addressed using the moment connection stiffeners. Now, all of the ones that we discussed so far, the web buckling, web crippling, yielding, and flange bending, these are all handled through transverse stiffeners. These are stiffeners that run from flange to flange and get welded on there in order to brace these flanges and these webs all against each other. The other failure mode that you'll run into is the panel zone shear failure. In the case of the panel zone shear failure, what we have here is a tension and compression acting on this column that results in a very high shear load in between these two resultant forces. And that very high shear load can actually cause a failure of the column web right here in shear just due to the large amount of shear that's been placed on it. So let's take a look at these within the program. What I'm going to do is I'm going to launch RISAConnection version 3, and we're going to take a look at a typical connection within the program. So I'm going to come up here to create new connections. Now you may also note, if you haven't used RISAConnection 3 yet, we have some additional connection types that are in here, including the direct weld and a variety of different splice connections that are new to the program. What I'm going to pull out is just our standard column beam flange plate moment connection. And this has been in the program since day one, but we've recently made some improvements to it relating to the stiffeners and the way that we handle column failures in this connection. So within this connection, if I come in here, I'm going to increase the moment load. What I'm actually going to do is set my units up here. You may not know this, but you can set the units in the program to be whatever you like, just coming up to the units up there, to inch kips. And I'm going to tell the program that I want to have 3,400 inch kips of moment coming into this connection. And what we'll find out as a result of that is that I'm going to get a number of failures in this connection. So we can see right in here a lot of the shear connection, or a lot of the shear limit states are all going to be fine because we didn't increase the shear on it, but with this large moment, we get a lot of failures on here. So one thing that I may want to do is increase the member size. The reason that I want to do that is if I come down here, certain aspects of this connection can all be addressed by increasing the thickness of connector plates or welds or bolts, things like that. But here I've got this flange plate, the beam flange tensile rupture. If my beam flange is failing in tensile rupture, then nothing I do with respect to these connector elements is going to help me, because what I'm getting is actually a tear out of my beam flange right up here. And the only way to solve that is to increase the area of the beam flange. So I'm going to come in here and take this W16 by 36 that I have, and I'm going to bump that all the way up to a W16 by 67. And what we'll find here now is that for beam flange tensile rupture, it will now pass because we have a larger beam flange, so that load can be spread out more. Now, coming into my 2D view, if I take a look at the top of the connection, we can see that my flange plate here is going to be not nearly as wide as the beam itself. And of course, you can just tell this looks like a goofy connection. So I'm going to click on the flange plate there, and I'm going to change its width to be 9 inches. And so by spreading that out, here we end up with more flange plate area, and we're going to need that area in order to be able to take the moment. So I'm going to come back into my reports here, and we'll see that the flange plate, in this case, is also failing in tensile rupture. And that may have something to do with the fact that the thickness of this flange plate is not nearly as thick as the flange now. So I would increase that flange plate thickness to 3/4 of an inch. And coming back in here, we are no longer getting the flange plate failure. However, we are getting a bolt shear failure at the flange plate. And so what we can do is come in here and add some more bolts in. Now at this point, I'm just getting this connection to work for everything except for the column limit state. So I want to go through here first off and start off with a reasonable connection so that we can then take a look at the effect of stiffeners. By adding in 6 bolts on the top on each side as opposed to 3, we increase the bolt shear capacity. Next, we have the weld strength that's causing us an issue. And so in this case, I've just got this little fillet weld on here. That's not going to be able to take these large amounts of flange force. So let's come in here, and as opposed to a fillet weld, I'm going to change that to be a PJP weld. And we'll try out maybe a 1/2 inch PJP weld. And you can see there's the 1/2 inch effective throat as opposed to the 3/4 inch thick plate. Coming back into my results here, I can see that we still fail even with this 1/2 inch PJP weld. That tells me we need to go larger, and if I'm going to go larger than a 1/2 inch on that, I may as well just call it out as a CJP. So in this case now, with the continuous joint penetration weld, we've actually got a full strength on there. And coming back into my connection under reports, we're passing for everything except for these bottom connection limit states down here. And these limit states are the column flange bending, web yielding, web buckling, web crippling, and panel zone shear. And so we'll take a look at these one at a time. The first one I have is the column flange bending. And let me just come back out here into the slideshow for a moment. We can see here's that flange local bending. This is the sort of failure that the program's telling us is occurring. And what we can see here is this is based off of a required and available force, and that's the flange force. So we need to have about 200 kips of capacity for that load on the flange, but we've only got about 141 kips of capacity in this case. There's a few different settings that we can consider in here. Certainly, the D end on here, this is the distance from the concentrated force to the top of the column. This is an input in our program here, and here's where we can input, this is the distance to the top of the column from the top of the beam. Certainly, if this connection is occurring up at the top of a column on the top story, then we don't have a whole lot of resistance because this flange can just bend right outwards from this location like it's shown in a 3D view. Whereas if this column goes up quite a ways, then we have some additional resistance on the top of the column there, and that's going to strengthen up the connection. In this case, though, we'll assume that that 20 inches is correct, and that goes up to maybe a splice or something like that on the column right above. We can see this is a fairly straightforward limit state. Here's the equation. This comes right out of the AISC, and so this is all just about the flange yield strength and the flange thickness. And so there's nothing that we can really do outside of bumping up the column size in order to eliminate this failure mode. And we'll come back to that in a moment. Next, let's take a look at the web yielding on here. Now, the web yielding, just like with the flange bending, is also failing. And you may note that we actually give you a hint in the program right here where we say add column web stiffeners, or modify the column size. And so in this case, with the web yielding, what we're taking a look at, that's this failure mode right here. This is based off of that N bearing area that we discussed earlier, and it's also based off of the thickness of the web and the strength of the web on the column in terms of the FY there. We can see that this also is not able to meet that capacity requirement. Next is the web buckling. Web buckling was this one. The whole web buckles outwards, and you can tell where that definitely would need a stiffener on the side of the web to be able to cover that one. And this one is just based off of the thickness of the web and the depth of the member. So this is just a pretty straightforward buckling equation. And you can see we're pretty close to passing on this one. It's only got a 1.02 unity check in that case. The web crippling, very similar to that one. This is more of a localized failure than the web buckling, but also the same idea that the column web buckles there. And we can see that we're also pretty close, and you can see this is a nasty equation right on here. This is one of these situations where having software available as opposed to doing it by hand makes your life a whole lot easier. And so we're failing on all these ones, and one option we would have certainly would be to bump up the column size, but let's presume maybe we're dealing with an existing circumstance where I can't change what the column size is because it's already in place. And oftentimes I should point out that AISC mentions that increasing a column size in terms of the weight of the column is almost always more cost effective than adding any sort of stiffeners or doublers. But let's say that we need to do this anyhow. What I'm going to do is I'm going to come over here to my connection properties, and on the transverse stiffeners I'm going to say yes. And so what this is going to do now is add these stiffener plates in on both sides of the column, and those are going to line right up with the flange plates. And these stiffener plates will serve not only to keep that the column flange from prying outwards, but they also brace this column web from any sort of failure that would occur in there. And so now if I come back into my reports, what you'll see is that those limit states right there, my column web yielding, buckling, crippling, these are all listed now as NA. So we can still see that the column would fail under flange bending because its capacity just isn't enough to take that force. But at this point, we're assuming that the column flange is no longer taking that force. Instead, that force is all being taken by those column stiffeners on there. And so for one thing, we come in here and we can see that there's certain geometry restrictions on this stiffener. And one of these restrictions that we have in here comes from AISC, the specification J10.8, which says that there's a minimum stiffener thickness. And by default, the program put in some 3/8-inch stiffeners on there, but those just aren't stiff enough. So I'm going to click on the stiffener in the 2D view here, and I'm going to bump that up to be a 1/2 inch thick. That ought to get us passing now for our geometry restrictions. So we have a minimum depth and a minimum thickness on that stiffener. And now at this point, rather than getting code checks for these limit states, which are no longer really applicable, we get code checks on the stiffener itself. So here's the stiffener yield and shear. We get a compression check, and we also get the weld strength checks on that stiffener as well. So if I come back out here, we can take a look at each of these. We can see here the program's put a 1/4 inch double fillet weld all the way around that stiffener, with the exception, of course, of the clips that occur here in the corner. So the program handles all that for us, and we've now eliminated those other failure modes. Now we still are failing for column panel zone shear though, and if we take a look at this one, we can see it's a little bit different equation because it's the shear failure of the column. Here we get the code call out in the equation, and so this is all just based off of the size of the web of the column here, and we can see we're failing by about 20%. And so I could just come in here as well and specify web doublers. So if I come in here and say web doublers yes, I'm going to get an error here because it's telling me I can't have both of them present at the same time. But coming back in here where I've got my configuration, I can have my web doublers on one side or both sides of the column here. And so this is going to take care of my column panel zone shear failure that I've got. And so right in here, this now becomes NA, and we get our code checks based off of the web doublers. So you can see you can come in here and set these up and control the dimensions or anything else that you like to do within them. And these are going to address a lot of those column failure modes that you previously saw in older versions of RISAConnection, where it would just fail you and you were sort of stuck at that you had your failure. So this is where you can control both of those settings right here under the transverse stiffeners and web doublers settings in the program. And this is available for all of our different moment connection types, or all the moment connections that go into columns anyhow, where we can come in and set any of this up. And if you have older RISAConnection models that failed due to any of those limit states, if you open them up in the new version of RISAConnection, you'll now have these options available, so you can update those older models accordingly. The next thing that I'd like to discuss in here, and here we go. This is just a summary of the flange stiffeners. These cover those limit states right there, and the web stiffeners are covering your panel zone shear. The next thing I would like to discuss is the non-concentric braces within the program. In the previous versions of RISAConnection, we have brace connections, but they have been limited to only concentric work points. That is, the center line of the column, the center line of the beam, and the center line of the brace all came together at one common point. And there's also been a limitation in the program that your gusset plate needed to stay within a certain aspect ratio. Now, that aspect ratio comes from the not the direct analysis method, but it comes out of a methodology that is prescribed in the AISC manual, and that AISC manual has the uniform force method. This is something that Dr. Thornton, I know, had a lot to do with coming up with. Larry Muir, I know, also had a lot to do with this one. And the AISC has been pushing this for the last few years. And the uniform force method, simply put, states that if you maintain a certain aspect ratio of your gusset plate, there will be no moment occurring anywhere within your connection, which makes the connection design very easy, because then we don't have to have any moment between the gusset and beam interface or the gusset column interface. And so what we do within the program by default is when you draw a brace connection in here, we place your load here at a distance halfway along the length of the gusset plate. I'll just enlarge this image here so we can see a little bit more clearly. And so that load is occurring halfway along the gusset plate, and then we restrict you to a certain height and width ratio in there. And that was the case in version 2 of RISAConnection. In version 3, though, we can now branch out and we can set the gusset plate to be any size that we want to. But how is that handled analytically? Well, in the case of the program, what we do is we will calculate the necessary ratio in order for you to have no moments present. And then when you increase, let's say the plate length, for example, by a distance that I'll call L prime here, what happens is your actual force, which is always going to occur at the center of the gusset, is going to move over by a distance of L prime divided by 2. And so we take a look at what would the ideal force location have been, where would that have been at this L over 2 distance, and where is the actual force occurring, and it's shifted over by this moment arm, L prime over 2. And so what we say is that there's a moment now that occurs, and that moment is just simply equal to the axial force that runs through this connection times that moment arm distance between these 2 points. And so you'll get the same forces running through your connection, but with an added moment that's going to occur at this location. Now, you could certainly also look at it the other way and say if I change my H in this connection, then I'm offsetting the horizontal force that's occurring between the gusset plate and the column. That would then have a moment arm, and so then we would see a moment that occurs due to that. Another big change in the newer version is that you can now specify the non-concentric work points, and that also results in a moment. So what we do here is we allow you to put the work point for the brace anywhere along the column or the beam, and then when it comes time to do the calculations, we calculate everything in this gusset plate according to the uniform force method, but then we also say that there's a moment that ends up in the gusset plate. And that moment is just simply equal due to the brace force multiplied by the eccentricity between the line of action of the brace and the concentric line of action of the brace. this occurs whether or not your work point is coming off of your column or off of the beam as well. So here we've got this brace that comes down, its work point is at the face of the column. It's also going to end up with an eccentricity on it as a result of that. And so that eccentricity will also have an effect on the design. I'm going to come out here into RISAConnection for a moment so that we can take a look at a brace connection and we can see how this occurs. So I'm just going to pull up a typical diagonal brace connection in here, and we can see that by default everything is set here to be on the uniform force method. And if I click on one of these gusset plate dimensions, here we can see I bumped that out to 36 inches. We see that the gusset height also increased. So anything that I punch in here is always trying to maintain that ratio, and that was the only option you had in RISAConnection version 2. In the latest version, version 3, you also have the ability to disable that. And you can do that down here under the width to length ratio setting on that gusset plate. You can see right now it's set to 0 moment for uniform force method. But I can come in here and set this to be unlimited instead, and then I'm free to make the gusset plate any dimensions that I want to without having to upset the other dimensions of the plate. This is ideal if you're going to be working with existing circumstances where you may not have control over what the gusset plate dimensions are. They are what they are, and you need to check this. And so this is really handy. Now, what you do run into as a result of this is because we've now violated the uniform force method, as I mentioned earlier, our force is now occurring in a different location from the idealized location, and the moment arm between those two locations is going to result in a moment on the connection. And we can see that when we come in and examine the individual connections on here. So if I take a look at the top gusset to beam connection, let's just go back out here for a second, the 2D view, that would be the connection between the gusset plate and that beam. We can see the forces that are involved in that connection. Here's an axial load of about 30 kips, a shear load of about 58 kips, but also notice that there's a moment in there of about 54-inch kips that's occurred due to that offset. And if I come back out here and increase that offset even more, what we're going to see is that moment is going to change as I pick out these different values. And so here, as we get further and further away from the ideal aspect ratio, this moment will continue to increase. And that moment does certainly penalize the connection design, but not necessarily that badly. As we can see, this connection still works just fine, even though we have that 145-inch kips of additional moment in there. Now, as for how that moment is handled, we will take that either to the beam gusset interface or the column gusset interface, or both. This comes from some white papers that we've read about in implementing this within RISAConnection. And what we discovered is that whenever there's a moment present in the connection, that moment is assumed to act through the more rigid of the two interfaces. So the two interfaces we're talking about here are the gusset beam interface or the gusset column interface. Now certainly if I have this direct weld connection here between the gusset and the beam versus some clip angles on the column, this gusset beam connection is going to be much more rotationally rigid than the gusset column connection. So it is assumed to take all of that force. Now I'm going to come in here and actually flip-flop those. So now here we've got a bolted connection to the beam, and we've got a welded connection to the column. And so now in this case, if I come back to my gusset beam connection, what we're going to see is that moment has dropped off to 0. But now if I go to the gusset column connection, it is now picking up the moment. And so the moment caused by that non-aspect ratio conforming plate is being carried directly through into the column rather than the beam. And so you can control it that way by just having one of these two connections more rigid than the other. Now what do we do in the case where both connections are equally rigid? Well, in this case, maybe I've got this whole gusset plate all bolted up. I wanted a completely bolted connection. There's no way for the program to know exactly how much rigidity that we have between one of these connections versus the other connection. So what we ask for is a user input in this circumstance. If I come back out here to my connection in this case, what we're going to find is that I get a certain amount of moment that comes through each one of these. Now, in this case, due to the uniform force method, we're able to estimate to some degree what that moment is, and so the program's actually smart enough to handle that. Where this becomes an issue, though, is when we get into the non-concentric situations. So let's take a look at this same brace connection here, where I come out to my work point, and rather than concentric, which I can set in the connection properties here, I say that I want this offset along the column axis. Well, now I have this extra offset in here. I have not only a non-conforming plate aspect ratio, but then I've also got a non-concentric work point, both of which are contributing moments. And these moments that we get within the gusset plate may be complementary in that they may be additive, or they may tend to cancel each other out. It all depends on the direction of the force, and we're running through all of that. So if I come back out here now that I've set that to be non-concentric, we can see here we get some pretty major moments occurring in both the gusset beam and gusset column connection. And coming down here, you'll see this is that setting that I was looking for before. This is the moment distribution setting. And so right now, by default, it's at 0.5, which means that 50% of the moment caused by that non-concentric work point is going to go into the beam gusset connection, and 50% is going to go into the column gusset connection. But I could come in here and say maybe I want the beam to take all of it. So then I would put that ratio all the way up to 1.0. And then here now, this is going to be taking a much larger moment. And if I come in here, you can see at this point, the top gusset to column connections dropped off all the way down to about 6-inch kips, whereas the beam has 711-inch kips of moment being placed on it. A fair amount, but still, when we take a look at the limit states on here, it's still not enough to fail that connection. So you can see here that I can set my work point along the column. I can also come in and set the work point along the beam as well. So I can tell the program that I want the work point anywhere along here. And in this case, here I've just got it set right at the face of the column, but I can come in here and control its location anywhere. I can even pull the brace back to here. I can get it away from the face of the column. If I have it along the column at any point, I can also control it through some settings in here. So here's my work point dimension. I can move it up or down along the column. So you can set your work point anywhere on here, which is ideal for modeling existing connections. And that's really what we were aiming to do with RISAConnection 3, was open up the flexibility of the program, allow you to specify anything that you may run into. Now, I'd like to also talk about the situation of integration with RISA 3D. So if we take a look at a brace, here I've got an example of a brace that I brought over into RISA 3D from Revit. And in this case, this is the physical arrangement that I actually plan to have. So I have a floor level that's 12 feet above this level here, and I want my braces to be concentric in this case. One of the issues that we run into as a result of this is that the actual angle between, say, the horizontal and that brace for how it's going to be constructed in real life is about 29.8 degrees. When I bring this into RISA 3D, though, this beam comes in at that 12-foot elevation, and the brace still stays concentric. And so what we get is this 30.9 degrees instead of the 29.9 degrees. That's about a 1-degree difference between how this brace is represented in RISA 3D and how it's actually going to be built. In terms of our analysis results, that 1 degree is pretty inconsequential. But when it comes to RISAConnection and the detailing that RISAConnection is going to do, that can actually be quite consequential. Now, what I did was I brought that model over into RISA 3D, and then I also set up a couple other example connections in here where we have non-concentric arrangements. And this is just to show you how to bring these non-concentric braces from RISA 3D into RISAConnection. What we can see here is, in this case, I've modeled this brace coming in a few inches below the beam column connection, and in this case the brace is coming off of the beam column connection a little bit. If I come in here, I'm going to show the connection rules. In this case, I've got under my connection design rules a diagonal brace rule that I've applied to both the beam and the brace. For the diagonal brace, you need to apply it to both of these. And what the program's going to do is If these two members share the same node, it's going to consider them concentric when it brings them into RISAConnection. If they don't share the same node, then the program is going to identify that this is a non-concentric bracing arrangement, and it's going to set the work points accordingly. So now when I solve this model for a batch solution and bring it over into RISAConnection using the director tool, what we'll see here is that the program has come up with these different arrangements for us. And so here is my concentric. Here is the one where the work point is coming off of the beam. And here's the one where the work point's coming off of the column. Now you may have also noted the program came up with the default gusset size for each one of these three, and the one where the work point is off of the column is actually far and away the most compact gusset size. This is very similar to what's known as the Uniform Force Method Special Case 1 in the AISC manual, where you can minimize your gusset size if you're willing to take a little bit of extra moment through these connections. So taking a look at the model here, one thing that I really did want to point out was about that angle. And so I showed earlier how the angle in RISA 3D doesn't actually match reality. In RISAConnection, we always take our angles from the vertical as opposed to the horizontal. And so what we would have here is a situation where the program thinks that the angle between the brace and the vertical is 59 degrees. But actually coming back out here, if I take 90 degrees minus that 29.88, we're going to end up with 60.12 degrees. What we've built into the program is the ability to override this angle that came from RISA 3D. So for the most part, things that come in from RISA 3D, such as the member size and such, can't be overridden once we get into RISAConnection. But I can come in here and make this more realistic. So I'm going to say, rather than using the angle that RISA 3D gave me, I want to use 60.12 degrees. And you'll see that it alters the geometry slightly. What's great about this is that now when I come in here and design my connection, if I export this out to AutoCAD, then the program is actually going to create my AutoCAD drawings that are going to be accurate. They're actually going to match what the real-life angles and configurations are on here, as opposed to my, say, approximated values that are coming out of RISA 3D. So that's just a really handy tool. But you can come in anyhow and create any of these connections that you like. You can set your work points anywhere now. You can set your gusset size anywhere. And then with the connections, the moment connections with the stiffeners, we really open things up a lot within RISAConnection. So I wanted to share these new features with you today, and also to let you know that we're actually already hard at work on RISAConnection version 4, and version 4 is going to be including a wide variety of tube connections. So keep an eye out for that one coming up.